Alright. Alright. I said. Alright. Alright. Are we ready? I said. I said. I said we fucking ready. I said we are. I said we
under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So here's the agenda for today. We're going to do a very quick review, and then we're going to introduce some very important concepts. The idea is that all information is always partial. And the question is, what do we do
¿Qué es esto,
to
weón?
probabilities if we have some partial information about a random experiment?
The important tools, multiplication rule.
Yeah, exactly what we did.
How this time?
We're going to introduce the important concept of conditional probability, and
pensé que era
then
una
we will
imagen
see
nomás,
three
weón.
very useful ways in which it is used. And these ways basically correspond to divide and conquer methods for breaking up problems into simpler pieces. And also one more fundamental tool which allows us to use conditional probabilities to do inference. That is, if we get a little bit of information about some phenomenon, what can we infer about the things that we have not seen? So, our quick review. In setting up a model of a random experiment, the first thing to do is to come up with a list of all the possible outcomes of the experiment. So that list is what we call the sample space. It's a set, and the elements of the sample space are all the possible outcomes. Those possible outcomes must be distinguishable from each other. They're mutually exclusive. Either one happens or the other happens, but not both. And they're collectively exhaustive. That is, no matter what, the outcome of the experiment is going to be an element of the sample space.
The what? The matter?
And then with the other happens, but not both, and they're collectively exhaustive. That is, no matter what, the outcome of the experiment is going to be an element of the sample space. And then we discussed last time that there's also an element of an art in how to choose your sample space, depending on how much detail you want to capture. This is usually the easy part. Then the more interesting part is to assign probabilities to our model. That is, to make some statements about what we believe to be likely and what we believe to be unlikely. The way we do that is by assigning probabilities to subsets of the sample space. So as we have our sample space here, we may have a subset A, and we assign a number to that subset, P of A, which is the probability that this event happens. Or this is the probability that when we do the experiment and we...
Oh, my bad. I thought it was P. That's a 3.14. It's not 3.14. It's just... Yeah.
get an outcome, it's the probability that the outcome happens to fall inside that event. We have certain rules that probabilities should satisfy. They're non-negative. The probability of the overall sample space is equal to 1, which expresses the fact that we are certain, no matter what, the outcome is going to be an element of the sample space. Well, if we set it up right so that it exhausts all possibilities, this should be the case. And then there's another interesting property of probabilities that says that if we have two events or two subsets that are disjoint, and we're interested in the probability that one or the other happens, that is, the outcome belongs to A or belongs to B.
What do you mean?
For disjoint events, the total probability of these two taken together is just the sum of their individual probabilities. So probabilities behave like masses. The mass of the object consisting of A and B is the sum of the masses of these two objects. Or you can think of probabilities as areas. They have again the same...
glitch, bro?
property. The area of A together with B is the area of A plus the area of B. But as we discussed at the end of the last lecture, it's useful to have in our hands a more general version of this additivity property, which says the following. If we take a sequence of sets, A1, A2, A3, A4, and so on, and we put all those sets together, it's an infinite sequence, and we ask for the probability that the outcome falls somewhere in this infinite union. That is, we are asking for the probability that the outcome belongs to one of these sets, and assuming that the sets are disjoint, we can again find the probability of the overall set by adding up the probabilities of the individual sets. So this is a nice and simple property, but it's a little more subtle than you might think. And let's see what's going on by considering the following example. We had an example last time where we take our sample space to be the unit square, and we said let's consider a probability law that says that the probability of a subset is just the area of that subset.
So like the whole
So
thing.
let's consider this probability law. Okay. Now the unit square is the set, let me just draw it this way. The unit square is the union of one element sets consisting of all the points. So the unit square is made up by the union of the various points inside the square. So union over all x's and y's, okay? So the square is made up out of all the points that it contains. And now let's do a calculation. One is the probability of our overall sample space, which is the unit squared. Now the unit square is the union of these things.
Unit square. What do you mean unit square?
Which, according to our additivity axiom, is the sum of the probabilities of all these one-element sets. Now, what is the probability of a one-element set? What is the probability of this one-element set? What's the probability that our outcome is exactly that particular point? Well, it's the area of that set, which is 0. So it's just the sum of zeros. And by any reasonable definition, the sum of zeros is 0. So we just proved that 1 is equal to 0. Okay, either probability.
Because that's not even within the A mass or the A circle. The oh shit, my bad. The gun. Yeah, finally. Yeah. Is it raining? Just a little. Nice. Total probability theorem. Period. What the fuck? Text it. The text it. Also, there's no glitches. Like what? False alarm. Oh yeah. Oh, that's just what it is, right? Oh, that's like like what we like what we did in the chess problem, or no, the false test, false positive. Good.
Probability theory is dead.
Yeah, understand now.
Or there is some mistake in the derivation that I did. Okay, the mistake is quite subtle, and it comes at this step. We sort of applied the additivity axiom by saying that the unit square is the union of all those sets. Can we really apply our additivity axiom? Here's the catch. The additivity axiom applies to the case where we have a sequence of disjoint events, and we take their union. Is this a sequence of sets? Can you make up the whole unit square by taking a sequence of elements inside it and cover the whole unit square? Well, if you try, if you start looking at a sequence of one element points, that sequence will never be able to exhaust. Well, if you try, if you start looking at a sequence of one element points, that sequence will never be able to exhaust the whole unit square. So there's a deep reason behind that, and the reason is that infinite sets are not all of the same size. The integers are an infinite set, and you can arrange the integers in a sequence, but a continuous set like the unit square is a bigger set. It's so-called uncountable. It has more elements than any sequence could have. So this union here is not of this kind where we would have a sequence of events. It's a union here is not of this kind where we would have a sequence of events. It's a different kind of union. It's a union that involves a union of many, many more sets. So the countable additivity axiom does not apply in this case because we're not dealing with a sequence of sets, and so this is the incorrect step. So at some level, you might think that this is puzzling and awfully confusing. On the other hand, if you think about areas the way you're used to them,
Hay un tío acá, weón. ¿Será un máster o una va así o...?
From calculus, there's nothing mysterious about it. Every point on the unit square has zero area. When you put all the points together, they make up something that has finite area. So there shouldn't be any mystery behind it. Now, one interesting thing that this discussion tells us, especially the fact that a single element set has zero area, is the following. Individual points have zero probability. After you do the experiment and you observe the outcome, it's going to be an individual point. So what happened in that experiment is something that initially you thought had zero probability of occurring. So if you happen to get some particular numbers and you say, well, in the beginning, what did I think about those specific numbers? I thought they had zero probability, but yet those particular numbers did occur. So one moral from this is that zero probability does not mean impossible. It just means extremely, extremely unlikely by itself. So zero probability things do happen. In such continuous models, actually zero probability outcomes are everything that happens. And the bumper sticker version of this is to always expect the unexpected. Yes?
But it's just very, very, very close to zero.
Well, probability is supposed to be a real number, so it's either zero or it's a positive number. So you can think of the probability of things just close to that point, and those probabilities are tiny and close to zero. So that's how we're going to interpret probabilities in continuous models, but this is 2 chapters ahead. Yep.
Interpret probability of zero in continuous models that way, then how do we interpret probability of one, that it's extremely likely but not necessarily for certain?
That's also the case. For example, If you ask, in this continuous model, if you ask me for the probability that xy is different than the point 0, 0, this is the whole square except for one point. So the area of this is going to be 1.
Fuck you.
But this event is not entirely certain because the 0, 0 outcome is also possible. So again, probability of 1 means essential certainty, but it still allows the possibility that the outcome might be outside that set. So these
The outcome might be. Oh, okay.
are some of the weird things that are happening when you have continuous models, and that's why we start this class with discrete models on which we will be spending the next couple of weeks. Okay, so now once we have set up our probability model, and we have a legitimate probability law that has these properties, then the rest is usually simple. Somebody asks you a question of calculating the probability of some event. Well, you were told something about the probability law, such as, for example, that probabilities are equal to areas, and then you just need to calculate. In this type of examples, somebody would give you a set, and you would have to calculate the area of that set. So the rest is just calculation and simple. All right, so now it's time to start with our main business for today.
Oh, really? Oh. Claro. Uh-huh. 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 Right. During into summation, this is exactly what you do discrete. What you do with discrete things, like right now. Mm. Wow. Wow, this is so interesting. To show that you can use summation in a continuous world. Wow. Oh, and I started using calculus integrals. Oh, calculus. Wow. Wow. Cool,
And
right?
the starting point is
Cool as fuck.
is the following. You know something about the world, and based on what you know, you set up a probability model and you write down probabilities for the different outcomes.
Yeah.
Then something happens and somebody tells you a little more about the world, gives you some new information. This new information in general should change your beliefs about what happened or what may happen. So whenever we're given new information, some partial information about the outcome of the experiment, we should revise our beliefs. And conditional probabilities are just the probabilities that apply after the revision of our beliefs when we're given some information. So let's make this into a numerical example. So inside the sample space, this part of the sample space, let's say, has probability 3/6. This part has 2/6, and that part has 1/6. I guess that means that out here we have 0 probability. So these were our initial beliefs about the outcome of the experiment. Suppose now that someone comes and tells you that event B occurred. So they don't tell you the full outcome of the experiment, but they just tell you that the outcome is known to lie inside this set B. Well, then you should certainly change your beliefs in some way. And your new beliefs about what is likely to occur and what is not is going to be denoted by this notation. This is the conditional probability that event A is going to occur, the probability that the outcome is going to fall inside the set A, given that we are told and we're sure that the event likely that event A is going to occur, the probability that the outcome is going to fall inside the set A, given that we are told and we're sure that the event lies inside the event B. Now, once we're told that the outcome lies inside the event B, then our old sample space in some ways is irrelevant. We have a new sample space, which is just the set B. We are certain that the outcome is going to be inside B. For example, what is this conditional probability?
1.
It should be 1, given that I told you
1/6.
that B occurred. You're certain that B occurred.
Oh, yeah.
So this has unit probability.
Yeah,
so here
you.
we see an instance of the revision of our beliefs. Initially, event B had a probability of 2 plus 1/6, that's 1/2.
Oh, my bad, yeah.
Initially, we thought B had probability 1/2. Once we're told that B occurred, the new probability of B is equal to 1.
Yeah.
Okay. How do we revise the probability that A occurs? So we are going to have the outcome of the experiment. We know that it's inside B, so we will either get something here and A does not occur, or something inside here and A does occur. What's the likelihood that, given that we're inside B, the outcome is inside B? Here's how we're going to think about it.
2/6.
This part of the set B,
No, my bad. 2/3.
in which A also occurred,
Yeah.
in our initial model was twice as likely as that part of B.
Yes, but now.
So outcomes inside here were collectively were twice as likely as outcomes out there. So we're going to keep the same proportions and say that given that we are inside the set B, we still want outcomes inside here to be twice as likely as outcomes there. So the proportions of the probabilities should be 2 versus 1. And these probabilities should add up to 0 because together they make the conditional probability of B. So the conditional probabilities should be 2/3 probability of being here and 1/3 probability of being there. That's how we revise our probabilities. That's a reasonable, intuitively reasonable way of doing this revision.
Right.
Let's translate what we did into a definition. The definition says the following, that the conditional probability of A that given that B occurred is calculated as follows. We look at the total probability of B, and out of that probability that was inside here, what fraction of that probability is assigned to points for which of B, and out of that probability that was inside here, what fraction of that probability is assigned to points for which the event A also occurs.
Okay, I don't know what you're talking about.
Does it give us the same numbers as we got with this heuristic argument? Well, in this example, probability of A intersection B is 2/6 divided by the total probability of B, which is 3/6. And so it's 2/3, which agrees with this answer that we got before.
Okay.
So the formula indeed matches what we were trying to do. One little technical detail. If the event B has 0 probability, then here we have a ratio that doesn't make sense. So in this case, we say that conditional probabilities are not defined.
Conditional probabilities are not defined.
Okay. Now you can take this definition and unravel it and write it in this form. The probability of A intersection B is the probability of B times the conditional probability. So this is just a consequence of the definition, but it has a nice interpretation. Think of probabilities as frequencies. If I do the experiment over and over, what fraction of the time is it going to be the case that both A and B occur? Well, there's going to be a certain fraction of the time at which B occurs, and out of those times when B occurs, there's going to be a further fraction of the a certain fraction of the time at which B occurs, and out of those times when B occurs, there's going to be a further fraction of the experiments in which A also occurs. So interpret the conditional probability as follows. You only look at those experiments at which B happens to occur, and look at what fraction of those experiments where B already occurred, event A also occurs. And there is a symmetrical version of this equality. There's symmetry between the events B and A, so you also have this relation that goes the other way.
Right. But okay. How I know this?
Okay.
So we use the probability of A to the ABA and then BABA. Okay.
So what do we use these conditional probabilities for? First, one comment. Conditional probabilities are just like ordinary probabilities. They are the new probabilities that apply in a new
You say conditional? Yeah, like unconditional, which is just a fucking probability.
universe where event B is known to have occurred. So we had an original probability model. We are told that B occurs. We revise our model. Our new model should still be a legitimate probability model, so it should satisfy
Look at this nigga. What are you doing?
all sorts of properties that ordinary probabilities do satisfy. So for example, if A and B are disjoint events, then we know that the probability of A union B is equal to the probability of A plus probability of B. And now if I tell you that a certain event C occurred, we're placed in a new universe where event C occurred. We have new probabilities for that universe. These are the conditional probabilities. And conditional probabilities also satisfy this kind of property. So this is just our usual additivity axiom, but applied in a new model in which we were told that event C occurred. So conditional probabilities do not taste or smell any different than ordinary probabilities do. Conditional probabilities, given a specific event B, just form a probability law on our sample space. It's still a probability in which we were told that event C occurred. So conditional probabilities do not taste or smell any different than ordinary probabilities do. Conditional probabilities, given a specific event B, just form a probability law on our sample space. It's still it's a different probability law, but it's still a probability law that has all the desired properties. Okay, so where do conditional probabilities come up? They do come up in quizzes, and they do come in silly problems. So let's start with this. We have this example from last time, 2 rolls of a die. All possible pairs of rolls are equally likely, so every element in this square has probability of 1 over 16. So all elements are equally likely. That's our original model. Then somebody comes and tells us that the minimum of the 2 rolls is equal to 0. What's that event? The minimum equal to 0 can happen in many ways if we get 2 zeros, or if we get a 0 and if we get 2 twos, or get a 2 and something larger. And so this is our new event B. The red event is the event B. And now we want to calculate probabilities inside this new universe. For example, you may be interested in the questions about the maximum of the two rolls. In the new universe, what's the probability that the maximum is equal to 1? The maximum being equal to 1 is this black event. And given that we're told that B occurred, this black event cannot happen. So this probability is equal to 0. How about the maximum being equal to 2, given that event B?
1.
Okay, we can use the definition here. It's going to be the probability that the maximum is equal to 2 and B occurs, divided by the probability of B.
Yeah, right.
The probability that the maximum is equal to 2. Okay, what's the event that the maximum
Only this, this, and this, right? No. Yeah.
is equal to 2? Let's draw it. This is going to be the blue event. The maximum is equal to 2 if we get any of those blue points.
Yeah.
So the intersection of the two events is the intersection of the red event and the blue event. There's only one point in their intersection. So the probability of that intersection happening is 1 over 16. That's the numerator. How about the denominator? The event B consists of 5 elements, each one of which had probability 1 over 16, so that's 5 over 16. And so the answer is 1 over 5. Could we have gotten this answer in a faster way? Yes. Here's how it goes. We're trying to find the conditional probability that we get this point, given that B occurred. B consists of 5 elements. All of those 5 elements were equally likely when we started, so they remain equally likely afterwards, because when we define conditional probabilities, we keep the same proportions inside the set. So the 5 red elements were equally likely. They remain equally likely in the conditional world. So conditional on B having happened, each one of these 5 elements has the same probability. So the probability that we actually get this point is going to be 1/5. And so that's the shortcut. Happened. Each one of these 5 elements has the same probability. So the probability that we actually get this point is going to be 1/5. And so that's the shortcut. More generally, whenever you have a uniform distribution on your initial sample space, when you condition on an event, your new distribution is still going to be uniform, but on the smaller event that we considered. So we started with a uniform distribution on the big square, and we ended up with a uniform distribution on just on the red points. Now, besides silly problems, however, conditional probabilities show up in real and interesting situations. And this example is going to give you some idea of how that happens. Okay. Actually, in this example, instead of starting with a probability model in terms of regular probabilities, I'm actually going to define the model in terms of conditional probabilities. And we'll see how this is done. So here's the story. There may be an airplane flying up in the sky, in a particular sector of the sky that you are watching. Sometimes there is one, sometimes there isn't. And from experience, you know that when you look up, there's 5% probability that the plane is flying above there, and 95% probability that there's no plane up there. So event A is the event that the plane is flying out there. Now you bought this wonderful radar that looks up, and you're told in the manufacturer's specs that additional probabilities, and we'll see how this is.
I'm getting fucking distracted, bro. Let me get a break. Let me get a fucking break. Let me get a break. Let me get a fucking break. Hombres, you say vibration thinking. Oh, I saw this video. Rey. Alright.
You probably don't realize it, but every time you change your mind based on new information,
Yeah.
like rethinking a decision after hearing a friend's advice,
Oh, you're
you're
talking?
using
Oh,
something
no.
called
It's a phrase.
Bayesian reasoning.
Bayesian.
Bayesian reasoning was first articulated by the Reverend Thomas Bayes,
Reverend.
a clergyman from Tunbridge Wells in southern England, way back in the 18th century. Thomas Bayes introduced two vital ideas. First, that our beliefs can be expressed as probabilities. And second, how our beliefs should be revised when we obtain more information. Alan Turing and his team at Bletchley Park used Bayesian ideas to learn about the settings of Enigma machines in World War II, changing their opinion as new patterns were found. The spam filter on your email account will use Bayesian analysis to change its probability that your email message is spam as each new suspicious feature is detected. Fundamentally, Bayesian ideas reflect what it means to be human. We live in a world of uncertainty, but we always have prior expectations of what might happen next, and we revise that uncertainty as we learn from experience. All based on the ideas of a rather obscure 18th century cleric from Tunbridge Wells.
Fucking Bayes.
You probably don't
Fucking Bayes, the Goaty. The Goaty. Ok. Mira, vamos a tomar un break. Pero como no soy malo, les voy a dejar un videazo.
The goal is for you to come away
There
from
you
this
go.
video
Have fun,
understanding
okay?
one of the most important formulas in all of probability, Bayes'
fun.
theorem. This formula, it's central to scientific discovery. It's a core tool in machine learning and AI, and it's even been used for treasure hunting. When, in the 1980s, a small team
Treasure
led by
hunting.
Tommy Thompson, and I'm not making up that name, used Bayesian search tactics to help uncover a ship that had sunk a century and a half earlier, and the ship was carrying what, in today's terms, amounts to $700 million worth of gold. So it's a formula worth understanding, but of course, there are multiple different levels of possible understanding. At the simplest, there's just knowing what each one of the parts means, so that you can plug in numbers. Then there's understanding why it's true, and later I'm going to show you a certain diagram that's helpful for rediscovering this formula on the fly as needed. But maybe the most important level is being able to recognize when you need to use it. And with the goal of gaining a deeper understanding, you and I are going to tackle these in reverse order. So before dissecting the formula or explaining the visual
Ой, мамаша, это больше ты хочешь, бей пошел.
listen carefully now. Steve is very shy and withdrawn, invariably helpful, but with very little interest in people or the world of reality. A meek and tidy soul, he has a need for order and structure and a passion for detail. Which of the following do you find more likely? Steve is a librarian or Steve is a farmer? Some of you may recognize this as an example from a study conducted by the two psychologists Daniel Kahneman and Amos Tversky. Their work was a big deal. It won a Nobel Prize, and it's been popularized many times over in books like Kahneman's Thinking Fast and Slow or Michael Lewis's The Undoing Project. What they researched was human judgments, with a frequent focus on when these judgments irrationally contradict what the laws of probability suggest they should be. The example with Steve, our maybe librarian, maybe farmer, illustrates one specific type of irrationality. Or maybe I should say alleged irrationality. There are people who debate the conclusion here, but more on all of that later on. According to Kahneman and Tversky, after people are given this description of Steve as a meek and tidy soul, most say that he's more likely to be a librarian. After all, these traits line up better with the stereotypical view of a librarian than a farmer. And according to Kahneman and Tversky, this is irrational. The point is not whether people hold correct or biased views about the personalities of librarians and farmers. It's that almost nobody thinks to incorporate information about the ratio of farmers to librarians in their judgments. In their paper, Kahneman and Tversky said that in the US, that ratio is about 20-1. The numbers that I could find today put that actually much higher, but let's stick with the 20-1 number, since it's a little easier to illustrate and it proves the point just as well. To be clear, anyone who is asked this question is not expected to have perfect information about the actual statistics of farmers and librarians and their personality traits. But the question is whether people even think to consider that ratio, enough to at least make a rough estimate. Rationality is not about knowing facts, it's about recognizing which facts are relevant. Now, if you do think to make that estimate, there's a pretty simple way to reason about the question. Reasoning behind Bayes' theorem.
Mis tamalitos acá en Caraballo te espero. Si no vienes, de la nariz sota te voy a jalar. ¡Ay, no!
Usted ya votó, ¿no?
Quiero a Federico, lo quiero a mi lado. Yo siempre lo he amado a él.
Siempre lo veo en las mañanas.
Claro, todos los días no me pierdo nada. Hasta lo veo en la petía, a la amanecida, igual lo veo. Todo el día lo
Estoy
veo.
emocionado hablando de Federico.
Ya sueño con él. Federico, ven a comer mis tamalitos acá en Caraballo te espero. Si no vienes, de la nariz sota te voy a jalar.
Bueno, tenemos un fiscalizador especial, ¿no? Aquí en esta mesa de sufragio. Te presento a Maya. Y Maya acompaña.
Overcome the fact that there are way more farmers.
Oh,
The upshot,
cállate,
and this is the
huevón.
key mantra underlying Bayes' theorem, is that new evidence does not completely determine. The goal is for you to come away from this video understanding one of the most important formulas in all of probability, Bayes' theorem. This formula, it's central to scientific discovery. It's a core tool in machine learning and AI, and it's even been used for treasure hunting. When, in the 1980s, a small team led by Tommy Thompson, and I'm not making up that name, used Bayesian search tactics to help uncover a ship that had sunk a century and a half earlier, and the ship was carrying what, in today's terms, amounts to $700 million worth of gold. So it's a formula worth understanding, but of course, there are multiple different levels of possible understanding. At the simplest, there's just knowing what each one of the parts means, so that you can plug in numbers. Then there's understanding why it's true, and later I'm going to show you a certain diagram that's helpful for rediscovering this formula on the fly as needed. But maybe the most important level is being able to recognize when you need to use it. And with the goal of gaining a deeper understanding, you and I are going to tackle these in reverse order. So before dissecting the formula or explaining the visual that makes it obvious, I'd like to tell you about a man named Steve. Listen carefully now. Steve is very shy and withdrawn, invariably helpful, but with very little interest in people or the world of reality. A meek and tidy soul, he has a need for order and structure and a passion for detail. Which of the following do you find more likely? Steve is a librarian, or Steve is a farmer? Some of you may recognize this as an example from a study conducted by the two psychologists Daniel Kahneman and Amos Tversky. Their work was a big deal. It won a Nobel Prize, and it's been popularized many times over in books like Kahneman's Thinking Fast and Slow or Michael Lewis's The Undoing Project. What they researched was human judgments, with a frequent focus on when these judgments irrationally contradict what the laws of probability suggest they should be. The example with Steve, our maybe librarian, maybe farmer, illustrates one specific type of irrationality. Or maybe I should say alleged irrationality. There are people who debate the conclusion here, but more on all of that later on. According to Kahneman and Tversky, after people are given this description of Steve as a meek and tidy soul, most say that he's more likely to be a librarian. After all, these traits line up better with the stereotypical view of a librarian than a farmer. And according to Kahneman and Tversky, this is irrational. The point is not whether people hold correct or biased views about the personalities of librarians and farmers. It's that almost nobody thinks to incorporate information about the ratio of farmers to librarians in their judgments. In their paper, Kahneman and Tversky said that in the US, that ratio is about 20-1. The numbers that I could find today put that actually much higher, but let's stick with the 20-1 number, since it's a little easier to illustrate and it proves the point just as well. To be clear, anyone who is asked this question is not expected to have perfect information about the actual statistics of farmers and librarians and their personality traits. But the question is whether people even think to consider that ratio, enough to at least make a rough estimate. Rationality is not about knowing facts, it's about recognizing which facts are relevant. Now, if you do think to make that estimate, there's a pretty simple way to reason about the question, which, spoiler alert, involves all of the essential reasoning behind Bayes' theorem. You might start by picturing a representative sample of farmers and librarians, say 200 farmers and 10 librarians. Then, when you hear of this meek and tidy soul description, let's say that your gut instinct is that 40% of librarians would fit that description, and that 10% of farmers would. If those are your estimates, it would mean that from your sample, you would expect about 4 librarians to fit the description, and about 20 farmers to fit that description. So, the probability that a random person among those who fit this description is a librarian is 4 out of 24, or 16.7%. So even if you think that a librarian is 4 times as likely as a farmer to fit this description, that's not enough to overcome the fact that there are way more farmers. The upshot, and this is the key mantra underlying Bayes' theorem, is that new evidence does not completely determine your beliefs in a vacuum. It should update prior beliefs. If this line of reasoning makes sense to you, the way that seeing evidence restricts the space of possibilities, and the ratio you need to consider after that, then congratulations! You understand the heart of Bayes' theorem. Maybe the numbers that you would estimate would be a little bit different, but what matters is how you fit the numbers together to update your beliefs based on evidence. Now, understanding one example is one thing, but see if you can take a minute to generalize everything that we just did and write it all down as a formula. The general situation where Bayes' theorem is relevant is when you have some hypothesis, like Steve is a librarian, and you see some new evidence, say this verbal description of Steve as a meek and tidy soul. And you want to know the probability that your hypothesis holds given that the evidence is true. In the standard notation, this vertical bar means given that, as in we're restricting our view only to the possibilities where the evidence holds. Now remember the first relevant number we used. It was the probability that the hypothesis holds before considering any of that new evidence. In our example, that was 1 out of 21, and it came from considering the ratio of librarians to farmers in the general population. This number is known as the prior. After that, we need to consider the proportion of librarians that fit this description, the probability that we would see the evidence given that the hypothesis is true. Again, when you see this vertical bar, it means we're talking about some proportion of a limited part of the total space of possibilities. In this case, that limited part is the left side, where the hypothesis holds. In the context of Bayes' theorem, this value also has a special name. It's called the likelihood. Similarly, you need to know how much of the other side of the space includes the evidence, the probability of seeing the evidence given that the hypothesis isn't true. This funny little elbow symbol is commonly used in probability to mean not. So with the notation in place, remember what our final answer was. The probability that our librarian hypothesis is true given the evidence is the total number of librarians fitting the evidence, 4, divided by the total number of people fitting the evidence, 24. But where did that 4 come from? Well, it's the total number of people times the prior probability of being a librarian, giving us the 10 total librarians, times the probability that one of those fits the evidence. That same number shows up again in the denominator, but we need to add in the rest, the total number of people times the proportion who are not librarians, times the proportion of those who fit the evidence, which in our example gives 20. Now notice the total number of people here, 210, that gets cancelled out. And of course it should, that was just an arbitrary choice made for the sake of illustration. This leaves us finally with a more abstract representation purely in terms of probabilities. And this, my friends, is Bayes' theorem. More often, you see this denominator written simply as P of E, the total probability of seeing the evidence, which in our example would be the 24 out of 210. But in practice, to calculate it, you almost always have to break it down into the case where the hypothesis is true and the one where it isn't. Capping things off with one final bit of jargon, this answer is called the posterior. It's your belief about the hypothesis after seeing the evidence. Writing it out abstractly might seem more complicated than just thinking through the example directly with a representative sample. And yeah, it is. Keep in mind though, the value of a formula like this is that it lets you quantify and systematize the idea of changing beliefs. Scientists use this formula when they're analyzing the extent to which new data validates or invalidates their models. Programmers will sometimes use it in building artificial intelligence, where at times you want to explicitly and numerically model a machine's belief. And honestly, just for the way that you view yourself and your own opinions and what it takes for your mind to change, Bayes' theorem has a way of reframing how you even think about thought itself. Putting a formula to it can also be more important as the examples get more and more intricate. However you end up writing it, I actually encourage you not to try memorizing the formula, but to instead draw out this diagram as needed. It's sort of a distilled version of thinking with the representative sample, where we think with areas instead of counts, which is more flexible and easier to sketch on the fly. Rather than bringing to mind some specific number of examples like 210, think of the space of all possibilities as a 1x1 square. Then, any event occupies some subset of this space, and the probability of that event can be thought about as the area of that subset. So, for example, I like to think of the hypothesis as living in the left part of the square with a width of p of h. Now, I recognize I'm being a bit repetitive, but when you see evidence, the space of possibilities gets restricted, right? And the crucial part is that that restriction might not be even between the left and the right. So the new probability for the hypothesis is the proportion that it occupies in this restricted wonky shape. Now, if you happen to think that a farmer is just as likely to fit the evidence as a librarian, then the proportion doesn't change, which should make sense, right? Irrelevant evidence doesn't change your beliefs. But when these likelihoods are very different from each other, that's when your belief changes a lot. Bayes' theorem spells out what that proportion is, and if you want, you can read it geometrically. Something like p of h times p of e given h, the probability of both the hypothesis and the evidence occurring together, is the width times the height of this little left rectangle, the area of that region. Alright, this is probably a good time to take a step back and consider a few of the broader takeaways about how to make probability more intuitive, beyond just Bayes' theorem. First off, notice how the trick of thinking about a representative sample with some specific number of people, like our 210 librarians and farmers, was really helpful. There's actually another Kahneman and Tversky result which is all about this, and it's interesting enough to interject here. They did this experiment that was similar to the one with Steve, but where people were given the following description of a fictitious woman named Linda. Linda is 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and also participated in the anti-nuclear demonstrations. After seeing this, people were asked what's more likely? 1, that Linda is a bank teller, or 2, that Linda is a bank teller and is active in the feminist movement. 85% of participants said that the latter is more likely than the former, even though the set of bank tellers who are active in the feminist movement is a subset of the set of bank tellers. It has to be smaller. So that's interesting enough. But what's fascinating is that there's a simple way that you can rephrase the question that dropped this error from 85% to 0. Instead, if participants were told that there are 100 people who fit this description, and then they're asked to estimate how many of those 100 are bank tellers, and how many of them are bank tellers who are active in the feminist movement, nobody makes the error. Everybody correctly assigns a higher number to the first option than to the second. It's weird. Somehow phrases like 40 out of 100 kick our intuitions into gear much more effectively than 40%, much less 0.4, and much less abstractly referencing the idea of something being more or less likely. That said, representative samples don't easily capture the continuous nature of probability, so turning to area is a nice alternative, not just because of the continuity, but also because it's way easier to sketch out when you're sitting there pencil and paper puzzling over some problem. You see, people often think about probability as being the study of uncertainty, and that is of course how it's applied in science, but the actual math of probability, where all the formulas come from, is just the math of proportions, and in that context, turning to geometry is exceedingly helpful. I mean, take a look at Bayes' theorem as a statement about proportions, whether that's proportions of people, of areas, whatever. Once you digest what it's saying, it's actually kind of obvious. Both sides tell you to look at the cases where the evidence is true, and then to consider the proportion of those cases where the hypothesis is also true. That's it. That's all it's saying. The right-hand side just spells out how to compute it. What's noteworthy is that such a straightforward fact about proportions can become hugely significant for science, for artificial intelligence, and really any situation where you want to quantify belief. I hope to give you a better glimpse of that as we get into more examples. But before more examples, we have a little bit of unfinished business with Steve. As I mentioned, some psychologists debate Kahneman and Tversky's conclusion that the rational thing to do is to bring to mind the ratio of farmers to librarians. They complain that the context is ambiguous. I mean, who is Steve exactly? Should you expect that he's a randomly sampled American? Or would you be better to assume that he's a friend of the two psychologists interrogating you? Or maybe that he's someone that you're personally likely to know? This assumption determines the prior. I, for one, run into way more librarians in a given month than I do farmers. And needless to say, the probability of a librarian or a farmer fitting this description is highly open to interpretation. For our purposes, understanding the math, what I want to emphasize is that any question worth debating here can be pictured in the context of the diagram. Questions about the context shift around the prior, and questions about the personalities and stereotypes shift around the relevant likelihoods. All that said, whether or not you buy this particular experiment, the ultimate point that evidence should not determine beliefs, but update them, is worth tattooing in your brain. I am in no position to say whether this does or does not run against natural human instinct. We'll leave that to the psychologists. What's more interesting to me is how we can reprogram our intuition to authentically reflect the implications of math, and bringing to mind the right image can often do just that.
A while back, I made a video about Bayes' rule and explained how it had been influential in my thinking. I didn't really, however, explain how Bayes' rule works, or what it is, so I'm going to do that today. I'll start with a puzzle. Imagine that you're walking across the campus of some large American university, and you meet a guy, let's call him Tom. You chat with Tom for a few minutes, and you notice that Tom is shy. He's not really making eye contact very often, he's mumbling. And my question for you is, if you had to guess, would you guess that Tom is more likely to be in a math PhD program or in the business school? Let's assume it has to be one or the other. So I don't know what you guessed, but I've taught a class on Bayes' rule a bunch of times, so I can tell you what most people guess, and that is that Tom is more likely to be a math PhD student. The reasoning is that shyness is just much more common in math PhDs than in business schools. And I think this is accurate based on my experience. There's an old joke that goes, how can you tell the extroverted mathematician? And the answer is, he's the one looking at your shoes instead of his shoes. Anyway, so I think that observation is accurate, but there's another piece of information that's relevant and that people tend to forget when answering this question, and that is, how many math PhDs are there relative to business school students? There's a lot fewer. The numbers will vary from school to school, but it's something on the order of 10 times as many business school students as math PhD students. So we have these two pieces of information about there being many more business students than math students, and also about shyness being more common among math students than business students. And the question is, how do we combine these two pieces to get one overall estimate about Tom? This is where Bayes' rule comes in. So you can imagine that this divided rectangle represents the relative proportions of math to business students, very roughly speaking. We'll put it at 1 to 10. And now looking just at math students, we can ask, how common is shyness? I would very roughly guess that it's about 75% of math PhD students come off as shy. And now looking just at business school students, again, guessing roughly, I'd say about 15% of business school students come off as shy. So now we've represented both of those pieces of information in one diagram, and we want to know whether Tom is more likely to be in a math program or a business program. We don't know which one he's in, but we do know that he's shy, which means that he must be in one of those lavender rectangles, right? Because those represent the shy math and the shy business students. So to get a sense of the relative probabilities of him being in math versus business, we just have to compare the relative sizes of those lavender rectangles. And it looks roughly like the lavender business rectangle is about twice as big as the lavender math rectangle. And you can see how the math shakes out. We just multiplied two linear ratios, the ratio of math to business students, which we put at 1 to 10, times the ratio of shyness in math versus shyness in business, which we put at 75 to 15. And multiplying those two linear ratios gives us a ratio of areas, which comes out to about 1 to 2. So roughly twice as likely for Tom to be in the business program, even though shyness is more common among math students. So this is the mechanics of Bayes' rule. This is how it works. And now I want to talk about how I use it in my everyday thinking. I don't plug numbers into a formula. I almost never draw these diagrams, in fact. But there are a few rules, principles of thinking that fall out of the math of Bayes' rule that are really useful.
Who is this beautiful girl?
Principle number 1 is something
Who
like...
the fuck is this beautiful girl? What the fuck are you even talking about? I don't know. Shy. Mad business. Don't be shy. I'm not dumb. Ok. 2, 3, 4 y...